Remember, for expert live tutoring in organic chemistry, email me at david.jeffrey422@gmail.com. Enjoy the video. Welcome to part 7 of the mini course, Preparing for Organic Chemistry. This is Spatial Aspects and Conformations. Look at this slide here, which depicts N-butane. If you remember when we talked about isomers, we said there were two butanes, N-butane and isobutane. At the very top of the slide, I have two different depictions, two different Lewis electron dot structures with the explicit hydrogens shown. And normally we would call those two representations identical, right? Because again, Lewis electron dot structures are not supposed to convey shape or geometry. But clearly the one on the right is not identical to the one on the left. They are different drawings. And if we forget for a moment that these are Lewis electron dot structures, then we can see that the one on the right is being generated by a bond rotation. A rotation, in fact, a 180-degree rotation about the central C2-C3 bond. Okay? And so, in fact, these are representations of, yes, the same identical molecule, N-butane. These are not isomers. Okay, but they're not identical molecules of N-butane. The molecule on the left has a fully extended shape, and the molecule on the right does not. These are conformations. Conformations. Now, multiple conformations of the same molecule are not isomers, but they're not identical. They're not necessarily identical. Okay, now, how do we know this? Because imagine that you are looking down. That's supposed to be your eye. Imagine that you are looking down that carbon-2, carbon-3 bond, okay, in both of these representations. And what you would see, and you should make a model. You should use your model kit and make a model and see this for yourself. What you'll see, though, if you look down that carbon-2, carbon-3 bond in that orientation, is you will see something that looks like the drawing on the lower left, right? For the left-hand representation of N-butane. And for the right-hand conformer, looking down the same bond, you will see something that looks like the representation in the lower right. The lower left is the staggered conformation of N-butane. Staggered. The lower right is the eclipsed conformation of N-butane. And these are good names. Staggered means just that. There's an alternating pattern of bonds that bisect each other. Whereas the eclipse conformation, you know what an eclipse is, right? That means on top of. And so we use this system, which is called Newman projections. These are Newman projections on the lower right to show conformational preferences or differences for the same molecule. So what we're saying is that these two conformations are not the same. They have different energetics. And so N-butane will be populated to different degrees by the conformation on the left versus the conformation on the right. In fact, let's take a little detour now. Let's point out that there are three geometric parameters that together can define unambiguously the exact geometry or shape, including three-dimensional shape, of any molecule, however large it might be, including macromolecules like proteins and DNA and RNA. And these are bond length, bond angle, that should be an E at the end, sorry, and torsional angle. Bond length, bond angle, and torsional angle. Now the conformations that we started to look at here in this lecture have to do with different torsional angles. So let's make sure that you understand exactly what these three parameters are. Here again is the molecule N-butane. Excuse me. And all I've done is I've labeled all of the atoms. Carbons 1, 2, 3, and 4, and then A, B, C for the hydrogens. And this allows me to unambiguously refer to any particular atom in this particular conformation in space. In fact, if you were entering the molecule into a computer program, this is what you'd have to do using the appropriate computer language or code, right? So let's talk about bond lengths. There are 4 unique bond lengths. You may say, well, that's not right. You know, there are a lot more atoms than 4 atoms. There has to be more than 4 bond lengths. Yes, there are more than 4 bond lengths, but there are only 4 distinct bond lengths, right? Because of symmetry, right? So in other words, the bond between carbons 1 and 2 is exactly equivalent to the bond between carbons 3 and 4. So we don't repeat that, right? The bond between carbon 2 and HA is exactly the same as the bond between carbon 2 and HB, so we don't repeat that. So these are the 4 unique bond lengths. How about bond angles? There are 1, 2, 3, 4, 5, 6. 6 unique bond angles. And you can convince yourself of this. And notice, by the way, that a bond length is always of the form AB. A bond angle is always of the form ABC. How come? Geometry. 2 points define a distance, 3 points define an angle, and 4 points define 3 dimensions. So when we get to the torsional angles, and yes, there are quite a few torsional angles, and they're all listed here, and I believe this should be complete and non-redundant, right? We have ABCD as a torsional angle, because what we're talking about is the angle between 2 planes, right? We're talking about, let's take the first torsional angle listed there, HA1, C1, C2, HA2, right? HA1, C1, C2, HA2 is the angle between the planes defined by carbon 1 and HA on carbon 1 and carbon 2 and HA on carbon 2. It's the angle between those 2 planes. That's what a torsional angle is. Okay, going back to our conformational analysis of N-butane, and again, use your models and convince yourself of this. If we can graph this. If we start with the staggered conformation that you see depicted in the Newman projection in the lower left-hand side of the panel, that's the same slide that you saw before. And if we keep the front group fixed and rotate the back group relative to the front, this is how we do this. Right? Keep the front group fixed and rotate the back group relative to the front, and we're rotating about carbon 2 and carbon 3. And if we start with the conformation on the left, and by the way, you can start with any conformation, all right? We're gonna perform 6 60-degree torsional rotations. 6 60-degree torsional rotations. 6 times 60 is 360. We're gonna go around a full circle and get back to where we started from. So if we start with this conformation, in this conformation, the staggered conformation, those methyl groups are as far apart as they can get, and that means that this is the preferred lowest energy conformation because the methyls are larger than the hydrogens. They require more space. They cause more electron repulsion. This is like Vesper. And so that is the preferred conformation of N-butane. So most N-butane molecules will be in that shape or conformation. And that's indicated by the energy bar in the graph, right, at 0 degrees before we do a rotation, right? The first 60 degree rotation, if you can imagine this and use your models to help you imagine this, you can do the rotations with your models. So if we rotate that back group 60 degrees clockwise, we'll do a clockwise rotation. Then what happens is that the back methyl eclipses with the front hydrogen, and we go up in energy. Eclipse conformations are always higher in energy than staggered conformations, because in eclipse conformations, the groups are, by definition, closer to each other. And so that first energy bar, 60 degrees, goes up. You can see it goes up in the graph. Another 60-degree rotation, and we go back to a staggered conformation. But it's not the best staggered conformation. The methyls are not as far apart as they can be, as they were in the starting staggered conformation. And so the energy bar drops down, but it's intermediate between the first staggered conformation, which is the lowest energy conformation, and that next eclipse conformation. That's why that bar is intermediate at 120 degrees. Okay, another rotation gives you the worst conformation. It puts the methyls in the eclipsed state. And that's why that bar goes all the way up to the very highest point. Okay, if you continue these 60-degree rotations, you don't generate new, unique, distinct conformations. You repeat the conformations that you saw before. They're the mirror images, and so the energies are identical, and you get this pattern. This is the pattern for N-butane, and we can go through this type of analysis with any simple molecule. With any simple molecule, we can go through this type of analysis. So just to finish the thought here, what this means for us is that if you have a large ensemble of N-butane molecules, right, in a beaker, right, you have trillions and trillions and trillions of molecules, okay, then, 95% of them will be in that original preferred staggered conformation, right, and a very small percentage of them, say, will be in that dimethyl eclipse conformation, and there's everything else in between. We can compute the exact percentages knowing if we know the actual energy differences between the conformational states, and we can get that information. Okay, so this is just a little bit of an aside. And so I said that we can go through this type of analysis for any simple molecule, okay? Appreciate that as the complexity of the molecule increases. Let's take a look at this as an example here, right? Okay, so here we have let's see, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, an 11 carbon compound or molecule, right, with a chlorine a substituent, with a hydroxyl substituent, with a double bond, okay? And yes, we can go through the same type of analysis, but we need help. We need help because appreciate that unlike N-butane, there are many, many more degrees of freedom, conformational freedom, because there are many more bond rotations that we have to look at. And so we need the help of a computer. And this is part of the area of chemistry called molecular modeling, which I have a background in, and which is fascinating. This is chemistry on the computer. And I'll just say that if you have an interest and are strong in not only chemistry, but physics, engineering, computer science, and to some extent biology, then molecular modeling is something that that might be of great interest to you for a career. But this is something that we need the computer to help us evaluate. And we need powerful computers to do this. These are complicated calculations. All right, now if you recall, several lectures ago we talked about isomers, and we started seeing, or actually even before isomers, when we looked at Lewis electron dot structures and the solutions to certain molecular formula, right? We saw for the first time a ring compound, a cyclic structure, right? I think we saw that for ozone, right? So ozone is O3, has a formula O3, and if you know nothing else about ozone except that it has the composition O3, then and you're asked to draw a valid and complete Lewis electron dot structure, okay, you're either going to draw the actual structure of ozone, which is three oxygens, okay, bonded together in a row or in a chain, or you're going to draw a three-member cyclic structure involving all three oxygens as well, bonded to each other. And they both satisfy the formula, and they both satisfy the octet rule, and there's no way to know which is correct unless you have other information about ozone. So it shouldn't surprise you that there are many, 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 many other cyclic structures in organic chemistry. Now, as far as their spatial aspects, do they have conformers the way, say, N-butane or a regular acyclic molecule does? And the answer is yes, they do, but they're much more limited. Because if you think about it, if the carbons are tied together in a ring, okay, you can't rotate freely about one carbon-carbon single bond without affecting the others. So this is an example of cooperative rotation. Let's take cyclohexane as a classical example in organic chemistry of cyclic conformational analysis. It turns out that the preferred conformation for cyclohexane is shown on the right-hand side of the panel, right? The first picture on the left is looking at cyclohexane from the top down. The second picture on the right is turning cyclohexane, right, out of the plane of the screen or the paper and looking at it side on. Okay, if you can imagine that perspective. And again, make a model and see this for yourself. And what we call that is, we call that the chair conformer of cyclohexane. Why the chair? Because it kind of looks like a chair. Looks like sort of a lounge chair, right? The left-hand portion is where your head goes. The right-hand portion is where your feet goes. It looks kind of like a beach chair or a lounge chair. This is the chair conformation of cyclohexane. Now, instead of free rotation about a carbon-carbon single bond like in N-butane, again, we have this cooperative rotation. And yes, there are two different chair forms for every cyclohexane, including cyclohexane itself. Now, for cyclohexane itself, okay, this is invisible because the two chair forms are identical, have identical interactions and identical energies. What becomes interesting is when you start replacing a hydrogen or hydrogens on the ring with a methyl, an ethyl, a chlorine, a bromine, okay? And so we talk about ring flipping for cyclohexanes. We talk about chair 1 on the left, flipping to chair 2 on the right. And you can do this flip with your models. And when you do this flip, you go through an intermediate conformation, which is very unfavorable, and that's called the boat. So we have the chair, which is preferred, and the boat, which is a high energy intermediate conformational state, which is depicted again in this slide. You can see it looks like a boat. And the reason that the boat is bad is because and I hope I've shown this adequately, for several reasons. Number one, you have those two hydrogens that are basically banging into each other at carbon 1 and carbon 4. It's a 1-4 interaction. Not only that, but you have eclipsing interactions on neighboring carbons, right? Carbon 1, carbon 2 have eclipsing interactions, and that's shown, and that's true also on the opposite side of the molecule. Compare that with the interactions in the chair. Now, the chair is not completely free of unfavorable steric interactions. In fact, in the chair we have what's called 1,3 diaxial interactions. Oh, let me just make this point. In the chair conformation of cyclohexane, you have what are called axial bonds and equatorial bonds. Now, axial bonds are those that stick straight up and straight down, and equatorial bonds are those that come off sort of at an angle, okay? And it varies around the ring. So if you're above the general plane of the cyclohexane ring, and you start, say, at carbon 1, okay, with an axial hydrogen pointing up, then as you go around the ring to the next carbon, the hydrogen that's still above the plane will be equatorial. Then you alternate again, back to axial, back to equatorial, back to axial. Make a model and see this for yourself. But we call this a 1,3 diaxial interaction because it's the axial hydrogens or any substituents that have replaced those hydrogens that are proximate through space and that can interfere with each other and can cause instability, right? Or can raise the energy of that particular conformation. So again, the two chair forms for cyclohexane are identical. It's when we substitute one or more hydrogens for substituents or attachments that those two chairs become differentiated. What about other ring sizes? Well, here's the 5-membered ring cyclopentane. Looking at the upper left representation, this is looking at the molecule from the top down, again implied hydrogens. Looking at the upper middle representation, cyclopentane is not a flat molecule. If it were a flat pentagon, you'd have eclipsing interactions all the way around the ring, which is what I've tried to point out. So what cyclopentane does is it deviates away from planarity and forms what's called an envelope type conformation, which I've tried to depict in the upper right, which minimizes the eclipsing interactions. What I show on the bottom of this slide is cyclodecane, right? Now we go to a larger membered ring, and what I'm showing is that you have in these, this is actually considered a medium membered ring, and what you have in these medium membered rings, 8 membered, 9, 10, 11, you would think that those rings would have very few negative interactions because they're larger rings and should have more degrees of freedom. But it turns out that because, say, cyclodecane wants to adopt a kind of pseudo chair, right, conformation, right? You can imagine that cyclodecane is 2 fused cyclohexanes with the middle bond deleted, right? And therefore, to the extent that it is cyclohexane-like or double cyclohexane-like, it's going to want to be in that pseudo chair type conformation. The problem with that is those hydrogens that you see there that I've indicated at carbons 1 and carbon 6, right, cause what's called transannular across a ring. Annular is ring, transannular strain. And you get a pattern if you look at ring size versus total strain. You get the following pattern. You get this pattern here. So what are we looking at here? Okay, so on the x-axis we have ring size, okay, and the smallest membered ring is of course a 3-membered ring, and on the y-axis we have total strain energy, total unfavorable energy. And that would correspond to any eclipsing type interactions. It would correspond to any through space steric interactions, say 1,3 diaxial in the 6-membered case, or transannular strain in the 10-membered case, which we just saw. What is also included in this total strain energy is what's called bond angle strain. Now, we haven't talked about bond angle strain, but let me just tell you, I think you can appreciate that for small membered rings, like 3 and 4, cyclopropane, cyclobutane. Okay, by the way, you can see how unfavorable those are right in this graph. I mean, cyclopropane has 27.6 kilocalories. That's not kilojoules, kilocalories, right? So multiply that by 4 or so to get kilojoules. That's a lot of strain energy. And then cyclobutane is right after it, and then it drops all the way back down to about 6.5 for cyclopentane. Cyclohexane is set at 0, but just realize that cyclohexane is not a completely strain-free molecule. We talked about the 1,3 diaxial strain. So where is this tremendous strain energy coming from for cyclopropane and cyclobutane? And it's coming from the fact that the bond angles, imagine cyclopropane. I don't have a picture of it, but imagine cyclopropane, right? Make a model of cyclopropane. Okay, you're going to have a hard time making a model because the bonds don't want to connect. They don't want to connect because your model kit knows that these are tetrahedral sp3 carbon atoms that want 109.5 degree bond angles. Well, you can't have a 109.5 degree bond angle in an equilateral triangle. It's geometrically impossible. But the bond angles aren't 60 degrees either. The internuclear angles may be 60 degrees, but the bonds actually bend away from that to do their best to approach the ideal tetrahedral bond angle, or sp3 bond angle, of 109.5. They're not 109.5, they're less than 109.5, and that's where the strain energy comes in. Okay, but notice the pattern here. So we leave the 3-membered rings and 4-membered rings, small rings, which is a special case of bond angle strain. We go back down to the 5-membered ring. You can see it there at 6.5, and that is due again to partial eclipsing interactions in this envelope conformation. We get down to the reference, which is the 6-membered ring, which is the most stable ring size in nature, in biology. And then we jump back up to 6.3 for the 7-membered ring and 9.6 for the 8, and so on and so forth. That, you see, that rise again after the drop to the 6-membered ring, that rise back up to, what is it, 12.6 or so for the 10-membered ring. That again is the transangular strain, and so it's quite, you can see it's quite significant. But as rings get even larger, as we leave, 10, 11, 12, and get larger, well, actually once we get to 12, right, it drops way down again, and it keeps going down, 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 because again, now you're into large rings, and large rings really do have a lot more conformational freedom and many more degrees of freedom, and they can kind of get out of each other's way. The atoms can kind of get out of each other's way in terms of the torsional angles, and what you see again is you're really back to, by the time you get to, these very large rings, 16, 17, 18, 19, it might as well be an acyclic chain, right? It doesn't really behave even like a ring anymore. All right, so I think we're going to stop there, and I'll probably do another lecture on spatial aspects. There's a lot to this. But I urge you to use your model kits if you don't have a model kit. And I apologize. I mentioned, I think, in the previous lecture that I was going to include in the description of the video a link to a model kit. So I'll be sure to do that in both in this video and in the previous one as well. You need to get those model kits. All right, take care. Remember, for live tutoring in organic chemistry, just email me at david.jeffrey422@gmail.com. I hope you've enjoyed this video.